Hello. I wanted to take a look at two seemingly different but actually related rates problems. These are pulled out of Stewart's Calculus, 7th edition, so the problem numbers are maybe different by now. We're going to take a look at these. The first one is this. A boat is pulled into a dock by a rope attached to the bow of a boat passing blah, blah, blah. The important thing is it's going from the bow of the boat to a point 1 meter higher than that point. If the rope is pulled in at 1 meters per second, how fast is the boat approaching when it is 8 meters from the dock? We're also going to look at this problem, which is number 11 from that same section. A plane flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour passes over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles from the station. We're going to take a look at this one first, and then we'll take a look at the other one. This is a nice example of two problems looking very different superficially, but actually having very similar solutions. So, in this problem, a plane is flying horizontally at an altitude of 1 mile at a speed of 500 miles per hour, passes over the radar station. And so the idea here is here's our radar station. Here is our plane. It is traveling over the radar station, and so in our picture it's going to be moving to the right because it has already passed over it. And so that distance that we're interested in, that 1 mile is this, and that stays 1 mile. It takes the time to actually mention the horizontal motion, which implies a horizontal, a constant altitude. Now, while they mention this 2 miles from the station idea, it's not always 2 miles. It's a moving plane. This distance from radar station to plane is varying, so we should give it a variable. That's an x. And so what we see here is that 500 miles is really a dx dt of 500. That's that 500 there. And what they want is the distance from the plane to the station. Now, this is a little bit vague because do they mean the horizontal distance, like if you're looking top down, or do they mean this straight line distance? Well, in this case, the distance from the plane to the station, well, if you just wanted the horizontal distance, that's what that 500 is. That's probably not what they want. They want this here. Well, that's a distance that we're interested in. It's a distance that's changing, so we'll call that z. And so they want is dz dt when, and now here's a problem with this statement as written, when it is 2 miles from the station. Now that is a bit vague because do they mean 2 miles the way you normally measured miles for distance for planes, or do they mean straight line distance? So is that really x equals 2? Or is that z equals 2? And the problem doesn't really give you a way of doing it. I think both of these are valid readings of the problem. Looking at the answer in the back of the book, they mean the z equals 2, but I'm actually going to go through both of them. So let's actually work through it. And we're actually done with reading this. I don't need the statement of the problem anymore. We'll want to come back around to it at the end just in case there's some subtleties that we've missed, but the bulk of the work is right here in front of us. So we have a dx dt, we want dz dt, and so what I have here is I need to relate x and z. I've got a right triangle, and so Pythagorean theorem, I don't care about angles in that right triangle, so I don't need trigonometry. Pythagorean theorem seems to be the thing I want. So 1 squared plus x squared equals z squared. I guess I could simplify that 1 squared, but in the end I'm going to be taking the derivative of both sides with respect to time, as we always do with related rates problems. And so it's be 1 squared plus x squared. Do our derivatives. Derivative of a number is 0. That is 2x times dx dt. Because the x and the t don't match, the x is changing with respect to time, and so chain rule says that ought to be there. It's really x of t. And if you take the derivative of x of t, that should be x prime of t. But if it was x prime of t squared, it would be 2 times x of t to the first times an x prime of t. So that's what that dx dt is doing. It's that chain rule of the inside function. It doesn't look like a function though. Anyway, moving on. Derivative of this z squared is again 2 times z times dz dt for the exact same reasons. They want dz dt, so I'm going to go ahead and solve for that a while. So dz dt is 2x over 2z times dx dt. Those 2's divide to 1. And now I can actually worry about substituting. You can sometimes substitute back here, but since there's two different things I wanted to substitute, I thought I would get all the way down to this point here. So if x is 2, what we're looking at is 1, 2. And so that would imply, by Pythagorean theorem, that z would be square root of 5. It would be square root of 1 squared plus 2 squared. All right, so if that's the case, then if it were the x equals 2 interpretation with the horizontal distance being 2 miles, then dz dt would be x is 2, z is square root of 5, dx dt is that 500, and so that would be 1,000 over square root of 5. And if you actually take time to rationalize the denominator, you would get 200 times square root of 5. Compare that to, and that would be your final answer. That would be the rate at which z is changing. And that would be, everything else was in miles and hours. So that, again, would be miles per hour. If we were looking at the z equals 2 interpretation, then we would be looking at a triangle 1, 2, and the thing that we want. And so what we need to do there is, again, Pythagorean theorem. That's going to imply that x is the square root of 3 once you go solving the Pythagorean theorem equation. And so dz dt equals 2 over, x is, back here, x is square root of 3, z is the 2, and that's the 500. And so now we have 250 times square root of 3. Now these aren't very, if you go down to the decimals and really look at what numbers these represent, they're not that different. But you know, a WebAssign or something that's, or a letter of the law kind of grader is going to want this one. It's a bit vague though from the way the problem is stated. I think either of them is a valid interpretation. All right, moving on to the other one that seems different but isn't all that different. Back to the boat is pulled into a dock by a rope attached to the bow. And so what we have here, I'm going to use a clean sheet. Here the boat, if we don't want that, the way the book is, picture of the book is drawn, we got the boat here, we got the top of the dock there, really the pulley that it's running from. That distance is not 1 mile, but rather 1 meter. The boat is moving in, and so this distance is changing, and this distance is changing as well. I'm going to use the same letters as before. It's the same picture, just turned a bit. It's a right angle there. And they give us the rope is pulled in at 1 meter per second. Well, that's the z is changing. This is the rope running on here. So now we're given dz dt is 1. Actually, we're given dz dt is -1 because the rope is being pulled in. And so that rope is shrinking, that distance is shrinking, and so you're losing 1 meter every second. Right. They want how fast is the boat approaching when it is 8 meters from the dock. Again, I don't think they mean the boat approaching along the z-axis, along the z line here. We want dx dt. And then they have the same, the same issue as the other problem, when it is 8 meters from the dock. Now, it's not the ambiguity that makes these two problems similar. It's the diagram. Let's take a look at the diagrams that we made before. And so we have, this was from the plane. No, I'm sorry, this is from the boat and the dock. And this is from the plane, but still, it's a horizontal distance, it's a vertical distance. These x and z are again related by, coincidentally, it's also a 1 in both cases. But it's going to be related by 1 squared plus x squared equals z squared in both cases. Before they gave a dx dt for the plane, for the boat, they give a dz dt, and they want the other one. But still, it's the same process. It's the same diagram. And so they want dx dt when, for the boat, when it is 8 meters from the dock. It's a little ambiguous as far as do they mean that z is 8 or when x is 8. But in either case, you don't use that 8 until the very, very end. Just like we never use this x equals 2 in the other problem until the very, very end. Do all your differentiation first and then substitute the values for the when. Let's just finish out this problem. X squared, 1 squared plus x squared equals z squared. Differentiate both sides, just like in the last one. 2x dx dt equals 2z dz dt. We're wanting dx dt. Fine. And so dx dt is going to be z divided by x times dz dt, already divided by 2 on both sides. And now they want 8 meters from the dock. Make this a little bit bigger. So when x is 8, for that interpretation, we're looking at 1, 8, and so our z is square root of 65. And so that would make your dx dt be z is square root of 65, 8, x is 8, dz dt is that -1, and so you get negative square root of 65 over 8, which is about negative 1.00, some ridiculously tiny number, different from 1, negative 1.7, blah, blah, blah. Or if they actually want the z equals 8, fine, we can do that. If z equals 8, then we're looking at that. That would imply that x, by Pythagorean theorem, running back through there, would be square root of 63, because that's the thing that makes 1 squared plus whatever this is squared equal 8 squared, which is 64. And so then the dx dt would be z, which is, we just said was 8, x, square root of 63, times dz dt, that -1, and so that's negative 8 over square root of 63. This is again about 1.007 ... Really, they differ by like 0.0002 between the two of them, which is like half the speed of a glacier. It's barely anything. The waves are going to have more effect. So the difference between those is very minimal, although again, grading by letter of the law, depending on how the problem gets read, only one of those would be considered quote-unquote correct. But it's vague as the problem's written. All right, thank you very much. If you have questions, you can post them in the comments. Thank you.